which we should be able to do. 2.5 is pretty short. And we just had one last thing to do in 2.4. So remember 2.4 was all about concavity again, concave up, concave down. So we had looked at determining whether a function is concave up or concave down based off of the graph. But now say we had this. So the one thing before I get there, this little piece at the top. So remember that the derivative is a rate of change, it's a slope. So that would mean that the second derivative is essentially a rate of change of rates of change. So it's essentially, you can think of it as the change in rate, sorry, that's not what I meant. The change in slopes. So you're looking at how a rate of change, which is a slope, changes. So say we have this table here, and it's in years and then numbers of car sales, and eventually we want to work up to talking about the second derivative, and I'm not drawing. And also there was a small typo on here that I forgot to fix. That should be dt in the denominator of that, because it should be the second derivative. But we want to work up to talking about the second derivative, but what we have in this table is essentially the original function, if you will. So if we want to talk about the second derivative, the first thing we would actually need to look at is the slopes. So that's why this first part actually asks us to find the average rate of change between each consecutive interval, because we're going to want to talk about the slopes. So why don't we find them first? So we will have a range in years. I'm going to make a completely new table versus the average rate of change, which I'm also going to just write as change in C over change in T, just kind of for giggles. Not really for giggles, but just to remind us that it is a change, a rate of change. So this table is quite long, so we've got a couple of these. So we've got 1972 to 1975, 1975 to 1980, 1980 to 1985, so on and so forth, 1985 to 1990, 1990 to 1995, 1995 to 2000, and 2000 to 2005. Whoops. So I'm only going to do 2 of these out in full generality, and then I'm just going to kind of fill in the table for time's sake. So if we're asked to find the average rates of change here, so the first one I want to find is the average rate of change between 1972 and 1975. Well, that would be our 1034 minus 587 all over 1975 minus 1972. That would give us a result of 149. And then again, I'm just going to write out the next one in generality, and then I'm just going to write down the actual values for the sake of time. So then if we want the average rate of change between 1975 and 1980, we've got our 1554 minus 1034 over 1980 minus 1975. That would give us 104. And then the rest of them are 7, 4, negative 50, negative 9.2, and negative 21.4. Found in the exact same way. I'm just not going to write them out in fullness for all of them, because that'll just take a little too long. So I'll hold on a second. If anyone's still writing that down. I'm recording. Yes, I'm recording. Okay. So now we want to take a look at the second derivative and the sign of the second derivative. Well, the second derivative, as I kind of already said, we want to essentially look at how the slopes are changing. Now, the answer to this question is going to sound very, I don't want to say it's wishy-washy, but there's going to be a decent amount of overlap that's going to make it seem weird. The reason there's such an overlap is because we are working over a range in years instead of just like a set value. If these were just set values, the overlap would just be over one single point, whereas the overlap we have here is kind of over a range of years. So, and you'll probably see what I mean in a second. But anyway, so let me look at these slopes in this table and try to figure out what's going on here. So if I start at 149, I can go all the way down to -50. And I could say that between 149 and -50, all of those values, yes, I can. Reshare, okay, yeah, this one's lagging a bunch. Come back, screen. There we go. So all of those values from 149 to -50, these are all decreasing as we go from left to right. And then if I kind of look at my next set, -50 to -9.2, and this is what I mean by there's lots of overlap. Those two values are increasing. We increase from -50 to -9.2, right? And then there's this unfortunate super overlap because then from -9.2 to -21.4, that would technically be decreasing again. So some of you might argue, well, you have a red line through essentially that whole entire table, so why isn't the whole entire thing decreasing? And again, it's that overlap is just because of the fact that we're working over these ranges. And so especially when I write the answer, it's going to be phrased really weirdly with all these overlaps. Say those were just numbers like 10, 11, and 12. We would say that they overlap at that single point. I feel like that makes more sense than trying to say that it overlaps over a range of years. So it's a bit ambiguous, which is unfortunate. But I hope that you would agree that there is these two numbers in here, -50 and -9.2, that is technically an increase. To get from -50 to -9.2, you had to increase the value. So anyway, the point of that is that we now have this idea of the slopes decreasing over certain pieces and then increasing over a certain piece as well. So if we start breaking those down, so we have that the slopes, because remember, these are slopes, they're average rates of change. So the slopes are decreasing over 1972 to 1995, and this is where the overlap sounds really weird when I start phrasing it like this. So the slopes are decreasing over that, range of years. So the second derivative is negative. Let me make my 2's match. And my pen's starting to freak out a little bit. I might have to switch to my tablet real quick. Ooh, threatening to switch to my other tablet might work. So since the slopes are decreasing over that interval, that means that the second derivative would be negative. That's kind of the relationship you want to pull, is if the slopes are increasing or decreasing will tell you whether the second derivative is positive or negative. So then in a similar way, we have that the slopes are increasing over, now again, this is where we've got these really bad looking overlap here. From 1990 to 2000. So the second derivative is positive on that interval. Here's my little thing that allows me to stop sharing. There it is. And why did it completely disappear? There we go. 2, 4. Hopefully you can see now. And then again, the slopes are decreasing over 1995 to 2005. So the second derivative, let me scroll down the tiniest bit, is negative on that interval. Let me say once more, and I'm going to write it down on the side for anyone who looks back at this later and might forget. We, how do I want to phrase this? Have overlap due to the x values, put that in quotes because technically they're t values here, are a range. So in general, if we weren't having those kind of x values, if you will, being a range, we would have seen something like an interval from like 1 to 5 being, you know, negative, and then 5 to 6 being positive, and then 6 to 8 being negative. So like the overlap would just be in those kind of singular points at the end. But since we don't have singular points as our x values, we have ranges. That's why the overlap seems obnoxiously bad and almost seems like it should just be decreasing everywhere, because we say from 1972 to 1995 and then also from 1995 to 2005. So that's kind of the reason for just that terrible, obnoxious amount of overlap. But so let me erase this bottom part. That might confuse people about where those numbers are coming from, and they were just made up. But that's kind of the idea that we want to pull from this example is just if slopes are decreasing, your second derivative is negative, and if slopes are increasing, your second derivative is positive. So let me even go one step further and just kind of underline those things, because that's the thing that we really wanted to pull from this example is just whether the slopes are increasing or decreasing gives us the sign of the second derivative. Questions, concerns on that example? All right, so that's the end of 2-4. Though I want to do one more that doesn't get into your notes, but so the second derivative is the derivative of the derivative. So back to 2-1, the one where we had the really strange Desmos and I had to like pop back and forth between a bunch of screens 5 million times. We found out that the derivative is actually a function. So since the derivative is a function, we can take its derivative. So essentially what the second derivative is, in the context that we care about, is it's essentially telling us how the slopes are changing over time. So the first derivative kind of tells us how the original function is behaving in terms of increasing and decreasing. That's how we kind of used that relationship to find the derivative value from, sorry, derivative graph from the original graph like you just did on your quiz. But the second derivative kind of tells us whether the slopes are increasing or decreasing. And so we kind of have these relationships between them where the second derivative is going to tell us whether the slopes are increasing or decreasing. And what that tells us about the original function is essentially if it bends upwards or bends downwards. So we kind of bring back this concavity idea that we got way back when from chapter 1. So the second derivative is going to tell us the concavity of a function. It's going to tell us whether it's curving upwards or downwards. So it's going to tell us kind of what situation we're in over here. So that's kind of what the second derivative is. It's the derivative of the derivative. So it's not just telling us how the function is increasing or decreasing, it's telling us how slopes are increasing or decreasing. So hopefully, maybe that helps a little bit. So I want to do one other example that didn't get into the notes, but is on your homework, and you technically have all the pieces you need to solve it, but a lot of people just don't see how to link the things together, so I want to talk about it really quick. So that screen's caught up with me, but that screen's not. Come on, there we go. Oh geez, I should have probably thought of this before right now, so now I'm thinking of it off the top of my head. Let's say that f of 4 is 6, and we know that f prime of x is f prime of 4, oops, is 3, and we know that the second derivative at 4, I guess. Maybe it just, no, I think it's usually just phrased in terms of x, and it just is that everywhere, I think. And what they then ask you is, what is a possible value of f of 8? And on Wiley, it gives you 3 choices. So, geez, let me try to think of 3 choices here. Give me 1 second. And 21. Sure. I think that worked. Hopefully I did that in my head correctly. Let me see. Yeah, okay, cool. So we want to know between these 3 possible values, 15, 18, or 21, which one's an actual possible value of f of 8? And this is kind of all the information we have to work with. So we know that f of 4 is 6, and we know that f prime of 4 is 3. So if you looked at kind of estimating f of 8 using that idea that we had from 2, 3, we could say that this is approximately equal to f of 4 plus 4 times f prime of 4, because 4 is 4 steps away from 8. So we would have 6 plus 4 times 3, so 6 plus 12, so 18. But we want to be careful here. So you might want to say maybe it's 18. That's not actually going to be the answer, but I'll tell you why in a second. So while that gives us an estimate of the value, the fact that we have this kind of new piece of information about the second derivative allows us to make a better estimate. Because if we think about kind of what this function might look like, or not even necessarily look like, but let's say here's f of 4. And if you think about what I'm doing when I'm calculating this kind of SUs over here, but remember that's technically kind of using that tangent line. So that's kind of using a tangent line, a straight line, to try to estimate f of 8, because it's, you know, going over 1 up 4 a bunch of times. But we're given this piece of information where the graph is, the second derivative is positive everywhere. Well, if the second derivative is positive, that would mean that f is concave up. Okay. And we also know that f prime is positive because it's equal to 3, and 3 is a positive number. And that means that f is increasing. So if I have an increasing function that's concave up, it's got to look something like this. And, well, now I regret writing those numbers over there. Let me try to move just those numbers. There we go. So the graph of the function has to look something like that because it's actually got a curve upwards. It's not going to actually follow that straight line. So our actual estimate, our better guess for what f of 8 would actually be 21. Because the fact that this second derivative is positive, meaning that the original function is concave up, kind of tells us how the function bends. So if it has to bend upward, then I'm actually going to end up being higher than my estimation from essentially using that tangent line approximation. Which I, now my really laggy screen is ahead of the other one. There we go. So remember, this kind of estimation that we did in 2.3 is called a tangent line approximation because that's exactly what it's using. It's using the tangent line, but the function doesn't necessarily follow the tangent line. So say, what if the second derivative had been less than 0? Then we would be increasing but concave down, so we'd kind of look like this piece here, so we'd look something like this. If it was less than 0, then our estimate would have been 15, because we end up kind of curving downwards underneath the tangent line instead of going above the tangent. Questions, concerns on that? That's a really good question. I really like that question, and it pops up on your homework. So now it should at least be familiar. Wait a couple seconds just in case. Okay, so then we're going to move on to 2.5. Where is 2.5? There it is. And come on, go. All right. So 2.5 is marginal cost and revenue. So up to this point in time, we've only talked about linear cost and revenue functions, but they don't have to be linear. They can be absolutely anything, any type of equation we want, or are given. So we want to be able to talk about, marginal cost, marginal revenue, marginal profit when it's not a linear function. So specifically consider the cost function really quick. So I know I'm saying that we can consider these things for all of them, but let's just consider the cost function really quick for our sanity. Then the y-intercept will be the fixed cost. Now I want to come off to the side really quick and do a side note. Now that screen's lagging. There we go. So fixed revenue and fixed profit. I don't want to say they don't exist, but they are not referred to as such. So if you were to say the fixed revenue, the fixed profit, someone would probably look at you super weird because it's not something that people actually, it's not, the verbiage is not used for revenue and profit. Does it exist? Technically, because those functions will have a y-intercept. So their y-intercept is still essentially telling us the revenue or the profit, of not selling any items. So it's still that idea of, even though they don't make anything, what's their revenue, what's their profit, which their revenue is probably 0 and their profit is probably negative. But so we don't really use the words fixed revenue and fixed profit. It's mainly just used for cost. But anyway, but then regardless of the equation, so now not just considering cost, but considering any of our cost, revenue, or profit, the slope will be the marginal cost, marginal revenue, marginal profit. So marginal can be used for absolutely anything. Used for all. So you can say marginal revenue and marginal profit, no one's going to think you're weird. Now, how do we find the slope if we don't have a linear equation? Well, that's what we kind of have just been learning. We can find the slope by using the derivative. If it hasn't linked in your brain yet that the derivative gives you a slope, make that connection. So the derivative being a slope is pretty much one of the most major things you need to recognize to be able to continue on. Derivative is a slope. So scroll down a little bit. There we go. Say we have this question here where we have the cost and revenue functions graphed for us. Now the revenue one is the linear one, the straight line. I think the labeling is a bit ambiguous, but the straight line is the revenue and the curvy one is the cost. And say I want to know what production values makes the firm profit. Like when do they actually start making money? Well, in general, if you would want profit to be positive, well, remember profit is revenue minus cost. So if I just replace profit with exactly what it's equal to, and then if I add cost over to the other side, I would get revenue is greater than cost, which you might have just thought of off the top of your head anyway. They have to bring in more money than they're, having to pay to other people. So where on this graph is that linear line have a higher y value than the curvy one? Kind of in this middle section right here. and they very nicely tell us what numbers those are. So I would say something like they make profit and I'm going to list it as an interval. So my Q values are between 130 and 215. Now notice that I don't include 130 and 215, and that's because at those 2 points I would essentially have 0 profit, so they'd be break-even points. And I don't want 0 profit, I want actual positive profit, so I want to make sure that I'm not including those 2 numbers in my answer. Alrighty. Couple more seconds before I scroll down. Okay. So let's say you work for a company, and let's say you sell mattresses. And your boss walks up to you and he's like, hey, we've only been making and selling 100 mattresses. Like we sell all of them, but we only make and sell 100 every, let's just say week for my sanity. Maybe that's a lot of mattresses a week, but anyway, we only sell 100 mattresses a week, and he wants to know whether or not they should start making more mattresses. Like, is that going to be a good idea for the company or not? They want to know. They come to you and they ask you to figure it out. So what would we really want to happen in that case for you to tell them that it would make sense for them to make an extra mattress? And usually in class, I'd make you think about it for a little bit and then answer me, but whatever, I'll just go with it. So essentially, if you think about it, if you want to increase your production, you would want to make sure that that's going to give you extra money and specifically extra profit. I don't care if I make extra revenue if, you know, my extra cost value completely eats that revenue. So we would want to make sure that, so we'd want to make more profit. I'm going to come back to this in a second. I kind of need this notation that we write down here to finish that. But we would essentially want to make sure that making any more mattresses is going to actually give you more profit. So some notation, because we're talking about marginal stuff here. So marginal cost will sometimes just be referred to as MC, but it's also the derivative of the cost function. Marginal revenue might be referred to as MR, but it's the derivative of the revenue function. And then marginal profit is the derivative of the profit function, which is pi, but we just usually, now you might see it as MP. I'll be honest, I don't think I've ever seen anyone refer to as MP. Marginal revenue and marginal cost are referred to MC and MR in Wiley a lot, but I don't think Wiley usually refers to marginal profit a lot. So you might not see that MP notation a lot. Also, one important thing about marginal profit is that it's also equal to the marginal revenue minus the marginal cost. It kind of mirrors that idea that profit is equal to revenue, revenue minus cost. So since regular profit is equal to revenue minus cost, marginal profit is equal to marginal revenue minus marginal cost. And I'll leave that side noted. And we'll box it. So coming back up to the thing above that really quick. So if we want to make more profit, essentially what you'd want is you'd want your marginal profit to be greater than 0. Because again, so the derivative is a slope. So if you think about what the slope is telling us, it tells us if we go over 1, how much we increase by, if you think about it in like that step way. So if we want to know, how much more profit we make by making the next item, we'd want to look at the slope at that point. So we'd want to make sure that that marginal profit would be greater than 0. Whoops. Hello, scroll back out. So kind of like that example above, that would also mean that the marginal revenue minus the marginal cost is greater than 0. Even let me put some errors in here. Which would also mean that we could swing that marginal cost over the other side. So we'd want marginal revenue to be greater than marginal cost. That Q does not look like a Q. So we're going to be asked a question like that a lot, where we're essentially asked, is it wise to make the next item? And this is what you essentially want to think about: is marginal revenue greater than marginal cost? Is marginal profit greater than 0? Now also, hold on 1 second. So also, approximately, marginal cost would be equivalent to C of Q plus 1 minus C of Q. And that also holds for revenue and cost. But in general, we will not use this to estimate C prime of something. So it is something that you might want to note, but you do want to pull on this idea of it being the derivative value more than this approximation value, because the derivative value, will be the exact value to the old example, like that far. What was I saying? Oh yeah, the derivative value will be, oh, down? There's not more to see? I'm confused now. Oh, was something in the way? Did the little thingamajig get in the way of your? Oh, okay. Yeah, that thing went away on my screen, so I kind of forget that sometimes it shows up. Anyway, what was I saying? So this kind of approximately idea is a nice thing to kind of have at the back of your mind, but we're going to be using the fact that it's equal to the derivative much more often, because the derivative value actually gets us the full correct value instead of an estimation. So we've got 2 examples and then we're done. We might get done the tiniest bit early. All right. And scroll. Now I also should have put on this graph. I should have put this on before I printed the notes, but I didn't. So there. So if we're given these 2 functions, graphed C of Q and R of Q, and we're essentially back to that idea of being at that mattress company where they want to know if they should make the 101st mattress. So should they make the 101st mattress? So your boss comes up to you and he's like, here's all the information I have on our cost and revenue, figure it out. And you're like, thanks, this isn't very helpful, but I'll try. So this is all we have to work with. Well, if you think about the fact that we only have cost and revenue, and we don't have any values, so we can't really find the value of profit here. So instead of thinking about the fact that we would want marginal profit to be positive, this is the piece where we want to kind of pull out the fact that that's equivalent to saying that the marginal revenue is greater than the marginal cost. And if we think about what those values are, well, remember the derivative is a slope. So if I kind of look at the slopes of these 2 functions, if I look at kind of the tangent line slope, at this value of R, and then let me change the color really quick, and then I look at kind of the slope of C. Well, if I compare those 2 slopes, which one of them is steeper? The black one is. So since the slope of R of Q is steeper than the slope of C of Q at Q equals 100, and I'll talk about why it's 100 in a second in case you're confused at why it's 100, not 101. So where am I going with this? The slope is steeper than that. So R prime of Q is greater than C prime of Q. So they should make the 101st mattress. I'll kind of put in parentheses because they make more money. just in case that wasn't clear. If marginal revenue is greater than marginal cost, then they essentially have made more profit than they were making before. And that's what we really care about here. Maybe I should ramble about that a little bit more too. So say you're selling these mattresses and you find that your revenue is, $10,000 for 1 week. And say you made the next mattress. So say instead of 100 mattresses, you decided to now sell 101 mattresses. Well, say your revenue your profit. I do want to talk about profit. I think I said revenue before. So say your profit for selling 100 mattresses was $10,000, but then your profit for selling 101 mattresses bumped down to like 9,500. Somehow making the cost of making that extra mattress is not made up in the revenue that it generates. So somehow, essentially, the revenue does not make up for how much it actually cost you to make that mattress. So even though you were still making profit, you didn't make any more profit, you actually made less profit. So that's why we want to look at the marginal profit. We want to figure out if we make more profit than we were before. Now, why am I looking at 100 instead of 101? Well, again, these are slopes. So if I want to know about how much I actually gain from the 101st, I want to look at the thing before it, because remember, a slope is essentially telling us if I increase the x values, the q values here, if I increase the q values by 1. So if I want to know about making the 101st thing, I have to look at the slope of the 100th thing, because that would tell me if I increase by 1 to the 101st item, how much my profit increases by. So that's why whenever you want to talk about should they make the whatever number item, you actually want to check the marginal profit of the number less than that, one number less than that. Hopefully that makes sense. Questions, concerns on that example, but we'll go on to the last one. Alrighty. So the last one is kind of similar, but now we've just got a cost function and we're just talking about cost. So we have this cost function. We want to answer these two questions. Look too far. Does it cost more to produce the 500th item or the 2000th item? So now notice that these Q values are in thousands. So if I want to look at the 500th item, that's going to be essentially at 1/2. And then the 200th item will be up at 2. So 2,000. Yes, because these numbers are in thousands. So if I want the 500th item, I'm essentially looking here. And if I want the 2000th item, I want to look here. Oh, is that your answer? Sorry, I might be dumb. So essentially here, I want to look and see which one costs more to produce. So I don't just want to look at their y values, I actually want to look at their slopes. So let me kind of look at the slope of the tangent line at both of those. So remember, if you have a problem, if you're having a hard time drawing a tangent line, pick a point, kind of right next to it, and draw the line between them. That's not an official way to do it, but it'll at least help you draw it. That second line is very hard to see. Let me try to bold that a little bit. So between those two lines, which one has a steeper slope? Well, the steeper slope is the one on the right, the one from essentially my 500th item. So actually, Kayla, it's going to be the 500th item. It has a steeper slope than 2,000. So we don't care about the fact that the cost is higher in general. We wanted to know about the cost to produce. So verbiage. Cost to produce. If you see the word produce, you can pretty much guarantee that they're trying to talk marginal cost there. How would they phrase? Why is my brain on how they would phrase just the regular old cost? I feel like they'd have to add in the word total. So maybe I shouldn't have underlined produce. Maybe I should focus on whether or not they say total. If it's kind of the total cost to produce or make or, whatever, then they're just talking about the generic. But if they're kind of asking you the price of making the next one, the cost to produce that many, and also, okay, so maybe another thing that helps us figure out that we're talking about C prime instead of C is it talks about the specific item. And usually, so let me add that in too. So also specific item. Whereas if they wanted to talk about the generic function, it'll probably be something like 500 items, or, they'll actually have the context in there, 500 shoes versus the 500th shoe. So that's another way to kind of tell the difference between whether or not they're talking about C prime or C. Anyway. So then let me switch colors for this one. Does it cost more to produce the 30,000th, not 30,000, the 3,000th or the 4,000th? Well, now I want to look up at, kind of just before 3 and then just before 4. So what's the slope at 3 versus the slope at 4? Which one of those is steeper? One at 4. So it would cost more to produce the 4,000th item. Now, I do want to be kind of clear on something. How do I want to phrase this? In the question beforehand, I was saying that it's important not to look at the exact value you're looking at, but the one before it. So some of you might be questioning, okay, well, if you want to talk about the 4,000th item, why aren't you looking at the slope of 3? Because these items are in thousands, we would want to know about the 4,000th item, so we'd want to essentially look at the slope of the 399th item. So based off of this graph here, that would be essentially, the tiniest bit to the right of 4. So just finding the slope at 4 in general is decent enough because of the fact that so the actual item underneath the 4,000th would be so close to actually just looking at 4 on this specific graph that it was okay for me to do so. If these values were just in like pure 1 items, then yes, I would have had to look at the slope of 3 versus the slope of 4. But since we're talking about thousandths, I don't want to look at the 3,000th item to talk about creating the 4,000th. To talk about creating the 4,000th, I would have wanted to look at the 399th item. And since that's so obnoxiously close to 4,000th on this graph, it's kind of okay that I just look at 4 instead of 3.999, if that made any sense, hopefully. So I just want to make sure that people don't think I'm going against what I was saying earlier about looking at the one before it. That still is something that you need to do, especially once we get into doing these kind of algebraically. You need to make sure that you're using the value before the one that you actually want to know about. Since we have a graph, we can be a little wishy-washy, especially it gets into a case like this where it's in thousandths instead of just one pure item. But you do want to have that in your mind of if you want to talk about the cost to produce the 40,000th, you technically want to look at the 399th. Hopefully that made sense. Questions, concerns on that? Okay. We got 5 minutes, so what I want to do super duper quick. I gotta pull it up really quick.
is I want to scan through your homework, just like I did with 2-4, which is why I did that random question, because I was like, oh yeah, that got on there and I forgot. So let me just scan through 2-5. There's not a lot of questions, so it will take me about 2 seconds. And see if there's anything else I should talk about really quick before we go. Oh yeah, maybe I should talk about that. Okay, so this one. I'm gonna talk about one more thing, and then we'll be done because I forgot that this type of thing sneaks on there. So let me pull off that. Come on, let me reshare. Can do it. There we go. One thing before this thing I talk about 2-5, you will want to use that idea of that tangent line approximation a lot. So that kind of idea, even though that was from 2-3, is going to be used in a decent amount of these 2-5 questions. That's where you're taking, like, you'll be given a C of Q and a C prime of Q, and you need to estimate values past that. But anyway, that's not what I want to talk about right now. So say I tell you that, let me just do it in brief notation. So revenue for 100 items, no, let's say 99, is, I don't know, 150, and revenue for 101 items is, I don't know, 220. Estimate the marginal revenue at 100 items. So super duper quick. So we had a question like this, phrased very poorly, but it gets the point across. So you're told essentially the revenue of like two item amounts, and then you essentially are asked to estimate the marginal revenue for a value between them, which in this case could only have been 100. So in general, when we were doing like that table stuff, when we were doing tables, don't know what that is, and we wanted to estimate the instantaneous rate of change, which remember gives us a derivative value, and the marginal revenue is a derivative. Remember, we kind of had to take the average rate of change on both sides and then average them. Well, in this case, we can't really do that because we don't know what the revenue at 100 is. So what we can do instead is, if we're missing this value here, what we can do is we can just take the average rate of change between kind of the two sides. So what you would do here is you're going to be able to estimate the derivative value at 100 by taking the slope between 99 and 101. So you'd have 220 minus 150 over 101 minus 99, whatever the heck that is. What is that, 70 over 1, so 70? I just did that in my brain, so that might be wrong. But essentially, if you have kind of the original function on kind of either side of the value that you want to talk about the derivative for, we can still use this idea of estimating the instantaneous rate of change. Using kind of those two sides. So we're officially done. If you need to leave, feel free to do so. Otherwise, I will be here for questions really quick. Now you should have all the things you need to complete your homework for this week. That's due on Monday. So have a great weekend. See you on Monday. 70 over 2. Oh, yeah. No, I'm dumb, Sam. Thanks. I was wondering, you said over 2, and I was like, I don't know what you mean by over 2. 220 minus, that was really dumb of me. 70 over 2, which is 35.
Wow, I'm dumb.